Welcome. This is John Limroth, LabVIEW Platform Manager. I'm here to present the using LabVIEW for interactive model-based control design and simulation. Before we jump into the tools, I'd like to talk a little bit about the application space of control applications. This slide here is an attempt to separate the application space of control applications into two separate areas. The first, shown over on the left-hand side, is where control is used to manufacture an end product. Examples of this would be industrial control applications, such as an oil refinery or food processing type applications, where control is used to manufacture the end product, but is not part of the end product itself. The second category is where control is actually embedded in the end product. For example, embedded controllers in airplane or automobile applications are typical examples. There is significant overlap between these areas, obviously. As shown on this slide, precision machine control is one area that encompasses a little bit of both control used to manufacture end product and control embedded in the product, such as embedded in the machine that's actually doing the control. The focus of this presentation will be on new tools in LabVIEW that extend LabVIEW into the model-based control design. Model-based control design is a process typically used in the design of embedded control applications. So a lot of our focus will be on applications that are on the right-hand side of this diagram. Although there is considerable overlap with industrial process control type applications as well, where these model-based control design approaches are being used more and more. So these same tools can now be applied to those industries as well. In the design of embedded control systems, where you can use model-based control design, the V diagram is typically used to represent this process. The details of the V diagram are not that important today, but what is important to recognize is the left-hand side of the V diagram represents the design portion, where you're creating the control algorithms and the logic that will go into the controller. This terminates with the code generation step down at the bottom, in which software is developed and embedded on an actual controller to go into the embedded control application. The right-hand side of this V diagram represents the testing side of the diagram. This is where the embedded software on the embedded controller is then tested and then integrated into the overall system and tested before final field testing and production testing. LabVIEW has traditionally been used in testing applications over on the right-hand side of the V. With the addition of LabVIEW Real-Time, we now have the capability to also use LabVIEW for rapid prototyping and hardware-in-the-loop testing applications, in which case control designs or plant models are embedded in a real-time system and interface with I/O to other parts of the overall system. The focus of today's presentation will be over here at the design and simulation step, in which case we'll be showing how these new tools for LabVIEW extend LabVIEW even further in this V design process into the actual design and simulation before deployment of control systems and testing of the overall embedded control system. This next slide shows an exploded view of that design and simulation step. The actual V diagram consists of many sub-steps. In this particular case, this is one particular model-based control design process. We'll talk about some of these individual steps in more detail in a minute, but the process you can go through is system identification, where you characterize the system that you're trying to control. The next step is control analysis and design, where you would design the control logic that will be used to actually control the system. Finally, simulation tools can be used to verify that the controller that you've designed provides adequate performance for the overall system. And then finally, this can be integrated with real-time for implementing the controller to control the real physical system, or for prototyping a control logic before it gets embedded on an actual application. This next slide shows these new LabVIEW tools and a different view on the interaction between system identification, control design, and simulation. As we'll see in a moment, the System Identification Toolkit provides the capabilities to use NI's data acquisition to stimulate the system that you want to control and measure the response coming back from that signal. With these I/O signals, System ID then can create a dynamic model of the system to characterize its dynamic response. This is the arrow coming out of these system identification algorithms up in the upper part of this slide. This model of the system you want to control, which is also referred to as the plant, then serves as the basis for the control design algorithms. So the system can be analyzed and an appropriate control algorithm can be designed for the particular plant model that you have. After this has been done with the control design toolkit, this then feeds into the LabVIEW simulation module, which allows us to do a closed-loop simulation of the overall system. In this case, the controller model output from the control design process then feeds into the LabVIEW simulation, as well as the model of the plant that was identified using the system identification toolkit. These can be simulated together in a closed-loop form, as shown in this diagram, to perform offline simulation and verify that the controller meets the required specifications. In addition, this same LabVIEW simulation module can be used together with LabVIEW real-time for implementation. So the diagram that previously had the plant model has now been replaced with data acquisition functions for output and input, such that the controller can be interfaced to the actual physical plant of the system that you would like to control. Before we get into a demonstration of these tools, I'll explain a little bit of the system that we're going to be using for the demo today. Specifically, what we're going to do is control the speed of a small DC motor. The particular DC motor that we're using is a training system provided by Quanser, who makes educational and industrial control experiments for teaching the basic concepts of model-based control design. In this particular case, we have an analog output signal coming from my PC to the DC motor to provide a command signal that feeds an amplifier that drives the DC motor. This little Quanser DC motor experiment provides an analog signal, tachometer signal, that corresponds to the speed of the DC motor, and we'll be measuring that back to control the motor to achieve the desired speed. As I already mentioned, the beginning of model-based control design is to characterize the dynamics of the system that you want to control, which is also known as the plant, which is shown here in this slide. The control design techniques that you will use the dynamic model of the plant as a basis for developing the control algorithms that will be used. There are several techniques to developing the dynamic system model of the plant, including mathematical modeling. From the physics of the problem, we can directly identify the differential equations and thus the dynamic system model that represent the plant dynamics, and include the physical parameters of the system with that mathematical model. The system identification toolkit provides an alternative means of modeling the plant behavior directly from I/O measured data, as we'll see in a moment. To use the system identification toolkit to identify the plant model, we first use the I/O capabilities of LabVIEW together with data acquisition hardware. As I mentioned previously, this is interfaced to the DC motor from the data acquisition hardware using analog output and input channels to provide a motor command signal to the DC motor and measure the speed back with the tachometer signal measured directly using an analog input on the data acquisition board. This motor command signal or stimulus signal will drive the motor and excite various frequencies of the motor, and by measuring the tachometer signal, we have a response signal that shows how the DC motor is actually responding to the command signal being sent to it. These signals together then feed into the system identification algorithms, which directly take the stimulus and response data and return a dynamic system model of the DC motor, which serves as the plant and our control application. I'll now switch to a demonstration of these tools using the system identification toolkit. The system identification toolkit adds functionality into the LabVIEW environment to perform system identification functions. In addition, the system identification toolkit provides a separate standalone interactive tool called the System Identification Assistant. This assistant is built within the Express Workbench environment, which is a which is in a common environment shared among several different National Instruments applications. If we go to the Help menu and look at About Express Workbench, it shows us the tools that are available within this common environment. So here we have the System Identification Assistant, which we will use to demonstrate the system identification algorithms. In addition, this includes the NI Signal Express product, which is a separate standalone product for interactive measurements and analysis in a workbench environment. We'll use NI Signal Express functions to generate a stimulus signal for the DC motor and measure the response signal coming back. We'll then use the System Identification Assistant to perform system identification and develop a dynamic system model from the measured stimulus and response data. Finally, we'll use the Control Design Assistant, which is the interactive part of the Control Design Toolkit, to design a controller for this system later on in the demonstration. Within this interactive environment, you create a project by adding steps, which are operations in which we tell the Express Workbench what we'd like to do. We'll start by adding a step to create a signal. I'll use a Signal Express function to create signal, in which case I'll specify that I want to create a square waveform, and I'll change some of the parameters. For example, instead of a 1 kilohertz frequency, I'll specify a 1 hertz, an amplitude of 2 volts to drive the motor. For my sample rate, I'll specify 1 kilohertz instead of 100 kilohertz. And for block size, I'll specify 3,000 samples, which in this case will correspond to 3 seconds worth of data. Whenever I close this step, I create an output signal called calculated signal. In this case, I'll rename this signal and I'll call it my motor input signal. I can then drag this signal over to the right-hand side of this Express Workbench environment, which is a data viewer pane, in which case when I drag the signal over, it immediately shows me what the signal will look like in time. As we add steps, we can add signals to this and provide an interactive way to view the data as we create our Express Workbench project. Next, I'll add a step that will use a Signal Express function to actually generate the signal on a data acquisition board using the NIDAC MX generate function. Whenever I create this step, I'll specify that I want to output my signal on my data acquisition board. In this case, I'm using an M-series multifunction data acquisition board, the PCI 6259. I'll specify on my generation I want to generate in samples rather than generating continuously, such that I only generate 3 seconds worth of data at one time. After creating that step, I can now add another Signal Express step that will allow me to acquire a signal. I'll use the NIDAC MX acquire signal step. Again, I'll use the same data acquisition board, and I'll specify that I want to acquire in samples. I'll specify 3,000 samples to acquire, just like I'm generating 3,000 samples, and a sample rate of 1 kilohertz. In addition, I can use the Advanced Timing tab within the step setup for the NIDAC MX acquire step to specify a timing source for the analog input operation. In this case, I'll use a common clock between my analog input and analog output operation such that the stimulus and response signals are synchronized in time when I perform my measurement. Once I've created that step, I can rename its output, which will be the acquired signal, to the motor output signal. I can then drag this signal over to my data viewer to add it here. In this particular case, I do not have any data yet because I have not run the actual data acquisition. I can use this Run Once button to actually run the DC motor, which will output the stimulus signal to the motor and then measure the response coming back. The red signal in this case is the acquired signal that's the response of the DC motor. Now that I have my stimulus and response signals, I can use the System Identification Assistant to actually determine the dynamic system model. The System Identification Assistant includes several functions for pre-processing of the data, model estimation where we actually determine the dynamic system model, and then analysis and visualization tools as well. In this case, I'll just use the core function, which is parametric estimation step, in which case I'll specify that my stimulus signal is the motor input, my response signal is the motor output. This now performs system identification to determine the system model. There are several different algorithms available for system identification. In this particular case, we'll use the ARX system identification algorithm for our DC motor. In addition, we can choose the model order settings for the order of the numerator and denominator coefficients of the ARX model. This particular model is similar in form to a discrete transfer function used in control and simulation applications. By increasing or decreasing the order, I can increase the accuracy of my system model. In this case, we can see that changing the A order from first order to second order provides a much better match between my actual motor output and a simulated output of the system identification model. We want to choose an order that is high enough to give very low error, but not unnecessarily high. In this case, second order provides an adequate response with very small error in our overall system model. I can close this. Once we've identified the system model, the parametric estimation step also outputs the estimated response of the system. So I can drag this estimated response over to my data viewer, and now I can see within one environment my motor input and output signals and the estimated response of the system identification model. Again, we can see that we have good agreement between the motor output in red that was measured with our data acquisition board and the estimated response in green from the system identification model. In addition, I can view the actual model itself by dragging the model signal over to the data viewer. In this case, because it's a different data type, it actually creates a separate window that shows us the system ID model, in this case, in a different form than the graph used for the waveforms that we were previously looking at. Here I can see the coefficients of this. Again, the A and B coefficients are similar to the numerator and denominator coefficients of a transfer function, representing the dynamics of this particular system. If we actually run the project again, it takes 3 seconds while it acquires data and then performs parametric estimation. And now we see slightly different coefficients in our system identification model output from the dynamic stimulus and response signals. To summarize the system identification toolkit, as I already mentioned, it also provides all of these types of functions directly within the LabVIEW environment as well. For example, we can use data acquisition functions in LabVIEW to create the stimulus and response signals, just as we did within the Express Workbench environment using Signal Express steps. In addition, we provide a VI, that's an interactive VI for doing system identification. This would be the parametric estimation that we did interactively, but provided as a LabVIEW VI with the toolkit. And as I mentioned, additional functions for analysis and model presentation are available within LabVIEW, such as you can create a LabVIEW VI to do all the steps of system identification as we just did interactively using the assistant. This provides a tight integration with all of the I/O capabilities available within LabVIEW, as well as the ability to create an interactive user interface using the LabVIEW front panel, as shown over on the right-hand side of this slide. We'll now switch over to creating a controller for our DC motor now that we've identified a dynamic system model of the plant. So the plant model can be used with analysis functions provided by the Control Design Toolkit to analyze the overall system response, for example, in the time domain or frequency domain. Once that has been done, the second step is to actually design a controller. So we provide design techniques in the Control Design Toolkit that, based upon the dynamic model of the plant, will allow us to design a controller for that particular plant. In addition, once we've designed the controller, we can take the overall closed-loop system of the plant model and the controller model together, and again use the analysis functions of the Control Design Toolkit to analyze the time and response characteristics of the closed-loop system to make sure that they meet the requirements and specifications that we had for our original embedded control application. I'll now go back to the Express Workbench project that we were working on, and now that we have developed a system identification model, I will now go and add control design to our project. In this particular case, I will add a step from the Control Design Assistant to perform root locus control design. The root locus method provides an interactive method of designing a controller based on the model of the plant. Specifically, the graph shown here is a pole zero map that gives us an indication of the roots of the closed loop system, which in turn give us information about the stability of the closed loop system and what type of response the system will give us. Initially, we provide only a feedback gain controller, and as we increase the gain of the controller, you can see that the assistant actually gives us an indication of when the system will go unstable at too high of a gain. If I reduce the gain, this indicator over here on the right shows us that the system will indeed be stable. For this particular system, I'm going to specify a more advanced controller that will have a pole located at 1 and a 0 located at 0.5 for this particular system. This will allow me to get closed loop response to the system in the form that I would like. Before we design the controller further, I'll go back to the project and add another step from the Control Design Assistant to actually view the step response of the closed loop system. To do this, I'll use the time domain analysis step. Here I can choose a time analysis to a step response or various other types of inputs. And instead of just the controller model, I'll specify the step response of the overall closed loop system model. In addition to my configuration, I'll specify a final time of 1 second for my simulation. I now see that my step response of the closed loop system has fairly oscillatory behavior, although it does settle out on the value of 1, which is the actual step input to the closed loop system. Once I've done this, I can actually create another display. In this case, I'll create a data view display below my previous displays, and I'll drag the step response over to the right-hand data viewer, in which case I can see my step response. If I now go back to my root locus design and go back to the step setup, I can actually view the step setup for the interactive root locus that will allow me to vary my gain, and then I can switch to my data view to see how that affects the time step response. So for example, I can see that at very low gain, my system has very low response, but has very little overshoot. Whereas as I increase the gain, the response to the step gets more and more oscillatory, but has considerable overshoot. In this particular case, I'll choose some compromise where maybe I have a little bit of overshoot, but a reasonably fast response rate for the system. In addition, once that I've created my controller model, I can add another view to my viewer. In this case, I'll add one to the right of the system ID model, and I'll drag my controller model over. This will allow us to view the actual controller model transfer function. If I resize these windows a little bit, now we can see the actual coefficients of the transfer function that comprises our controller in our closed loop system. This was what was developed using the root locus method, interactive method previously. In addition, I can add more steps in this project that will allow us to save both the system identification and the controller models. In this case, I'll use control design assistant functions to save the control design model. Here I'll specify a file to save this to. Specifically, I'll choose the motor model for my system identification model. And let me choose that path, the motor model, and then I'll add one more step, again a save control design model, and in this case I'll specify my controller model and specify a path to a file that I'll call motor controller. Now when I run once and look at the data, again I'm generating data, measuring the response of the system back, performing system identification, designing a controller, and then saving the response, both the system identification plant model as well as the controller model that we designed using the root locus method. I'll use these two models in just a moment within the LabVIEW simulation module to do both offline simulation of the overall system, as well as to create a controller that can be used in LabVIEW real-time to actually control this system. Switching back now to the slides, the LabVIEW Control Design Toolkit also provides functions within the LabVIEW environment for the analysis and design, such as the examples we just saw in the Interactive Control Design Assistant. By creating applications in LabVIEW, you can again use the front panel to create custom user interfaces for a particular control problem or class of problems. The next step, once we've designed a controller for our plant, is to actually do offline simulation using the LabVIEW simulation module. This will allow us to view a time response to the system to arbitrary inputs with advanced numerical solvers, as well as add a more high-fidelity plant model, for example, simulating nonlinear characteristics of the model or limitations of the controller, such as the output saturation. The LabVIEW simulation module allows us to represent closed-loop systems in control block diagram form directly within the LabVIEW diagram. We'll take a look at an example now of a LabVIEW VI where we've actually created a LabVIEW simulation that shows the closed-loop simulation. Here I'm using Control Design Toolkit functions to load in my motor model and my controller model. These can then be wired into this structure, which is a LabVIEW simulation loop provided with the LabVIEW simulation module. Within the simulation loop, we actually have the ability to represent control block diagrams directly. In this case, we have arrows on wires, and we have feedback structures directly within the simulation. Here I'm using a transfer function to represent our controller and a zero-pole gain model to represent the ARX model that we identified using the System Identification Toolkit. In addition, we have a signal generator function, in which case we can specify a waveform for the set points that we would like to generate for our simulation. Once we've created a control block diagram representation, we can use the configure simulation parameters function to specify various solver parameters. In this case, we have fixed step size and variable step size solvers available for the simulation module, as well as stiff solvers for the particular system. We can specify other parameters for the solver, such as the discrete time step and final time of the simulation. In addition to configuring these parameters statically for the simulation loop, I can also configure these programmatically. So outside of the simulation loop, I've created a control on my LabVIEW front panel that allows me to specify all of these parameters. Therefore, we can have an interactive front panel for this LabVIEW application where we can try different solvers and run the application. Now, whenever I run the application, it loads in the data from those files and applies a square waveform for the set point. In this case, it's performing purely an offline simulation that allows us to view how the system is responding to the overall simulation. I could choose different final times and solvers as well as step sizes to use in my simulation. Here I see, similar to my step response, I have some amount of overshoot, so I could go back to my interactive tool and refine my design somewhat to come up with a controller that responds quickly but has less overshoot. The simulation module provides functions for discrete and continuous linear systems, as well as nonlinear functions, functions for viewing the data, summation, gains, and so forth, and allows us to extend the LabVIEW environment by providing a control block diagram representation of the system directly within the simulation loop. This also provides tools for simulation that are already available in LabVIEW, such as graphical differencing and the user interface capability of the LabVIEW front panel, as we just demonstrated. Another important feature of this type of simulation within LabVIEW is the fact that within these simulation loops, we can use all of the functionality provided within LabVIEW itself. For example, all the basic logic and comparison functions within LabVIEW and programming structures can be used within the LabVIEW simulation loop, as well as I/O functions provided within LabVIEW. Another important feature of the simulation module is the Simulink translator. Since many people already have dynamic system models developed within the MathWorks Simulink environment, we've provided a tool that will allow you to reuse those models directly within LabVIEW by translating the model files into a LabVIEW implementation of those models. An example is shown here where we can specify a Simulink model, shown down in the lower left, and invoke the Simulink translator tool to then generate an equivalent LabVIEW VI for that Simulink diagram. Once we've performed offline simulation of the overall closed-loop system using LabVIEW's simulation module on a desktop PC, we can then use the LabVIEW simulation module together with LabVIEW Real-Time to actually implement the controller directly on real-time hardware, such as a PXI system or a compact Rio system. This slide here shows, again, the block diagram of our controller, but in this case we've replaced the plant model with analog output and analog input operations. So we can reuse the same LabVIEW simulation diagram, but just modify it slightly to use I/O functions available already within LabVIEW and LabVIEW Real-Time. And then the VI that we create that includes the LabVIEW simulation can be downloaded to a LabVIEW Real-Time hardware target, such as the PXI controller shown on this slide here. Using a data acquisition board or Rio boards interfaced directly to a DC motor, such as the example we're using here, we can then implement real-time control of that system. Thus, the LabVIEW real-time system can become the final real-time implementation of the controller, or it can serve as a rapid control prototyping platform for an embedded control application, or later on, a hardware-in-the-loop simulation platform by replacing the controller model with the actual plant model. I'll switch back to LabVIEW again quickly, and we can see an example of a control block diagram that could be used to implement our controller that we designed in LabVIEW Real-Time. Again, I can use functions to load in the motor controller model that we created using the system identification and control design assistance, and then a simulation loop that has been modified to replace the plant model with DAC-MX functions for input and output. So for example, I can use a DAC-MX write function to acquire an analog input point corresponding to the speed of my motor that feeds back into my controller by comparing to the set point to provide an error signal input to the controller. In this particular application, we've added a saturation block to ensure that the controller output doesn't exceed the limits capable of our data acquisition board. And then our data acquisition board provides a DAC-MX write function to actually output an analog signal that will drive the amplifier on the DC motor. In this case, we can, again, configure the simulation parameters. In addition, we can configure simulation timing parameters such that we can go in and specify a period to use, in this case 1 millisecond, that corresponds to the sample time used within the simulation itself. So we can actually implement a real-time implementation of this simulation, which is actually a controller implementation on our LabVIEW real-time target. In this particular case, I'm not connected to a LabVIEW real-time target that's connected to my DC motor, so we won't run this VI. To summarize, this simulation module together with the LabVIEW real-time module allows a tight integration with real-world I/O, either through DAC-MX functions and data acquisition boards, as we just looked at in the demonstration previously, or using LabVIEW FPGA technology with our Rio and compact Rio hardware platforms. Overall, this provides a seamless transition from offline simulation to real-time implementation, in which case the same exact code is being used in both cases, and that a LabVIEW simulation diagram can be reused both from the offline simulation to the real-time implementation. To summarize the tools that we've discussed in this demonstration, we looked at the LabVIEW System Identification Toolkit, the LabVIEW Control Design Toolkit, and the LabVIEW Simulation Module. These three tools are actually available together in one single bundle that is called the LabVIEW Control Design and Simulation Bundle to provide one part number for all of this functionality. In addition, this bundle provides additional tools, specifically the LabVIEW State Diagram Toolkit, which allows you to represent state machine logic directly in a state diagram form and eases the creation of state machine logic and can be used together with the simulation module for modeling hybrid systems and developing hybrid control systems. In addition, this bundling also includes the LabVIEW Simulation Interface Toolkit, which enables you to use Simulink models further, specifically by using LabVIEW as a user interface directly for the Simulink environment for offline simulation or real-time implementation on LabVIEW hardware, LabVIEW real-time hardware targets. To enable running Simulink models directly on LabVIEW real-time targets, the Simulation Interface Toolkit also allows you to use the MathWorks Real-Time Workshop tool to automatically generate a DLL from a Simulink model and then can be embedded on a LabVIEW real-time implementation that automatically calls that LabVIEW Simulink model to implement the model in real time, again for either implementation, rapid control prototyping, or hardware-in-the-loop simulation. This bundling of the tools also has the additional benefit of included one year of our standard service support, which is 1 year of free upgrades and phone support at any time on any of the tools included in the simulation bundle. This concludes our web event for today. For more information, please visit the website shown here and enter the code to find out more information about these tools, or feel free for us to call us at the number provided here. Thank you.